Greetings of the day to all of you. I welcome all my students for another series of lectures on a new course, new subject, which I am floating as an elective course for both MTech PEED, that's MTech Power Electronics and Electrical Drives, and MTech EPES, which means MTech Electrical Power and Energy Systems, first semester and third semester students. It's an elective course for MTech first semester as well as MTech third semester, both specializations of PEED and EPES. The title of the course is, let me write the title of the course. Excuse me, I was trying to introduce you to this course. The title of the course is Flexible AC Transmission System. Course title, I am writing here. It is Flexible AC Transmission Systems. That is facts. This is the title of the course, and course code. Course code is it is EEM128. EEM128. Okay, the course contains 3 credits. It's a 3-credit course. Credits 3 with lecture, tutorial and practical distribution as 3 lectures, and there are no tutorials, no practicals, although in between we can have a couple of some 2 or 3 tutorial classes also. Now regarding course contents. Okay, the topics that we will be covering in this course, which is also called course contents. What we have done, we have divided this course into 4 modules. Each MTech course we have divided into 4 modules. So we will have module 1, module 2, module 3 and module 4. So we have 4 modules. It will not be possible for me to write all the course contents. I will just read the course contents. This is the copy of syllabus with me. Module 1. In module 1 we will be covering following contents. Introduction to Facts Technology. In fact, that is the first class which I will be delivering today. I will try to introduce you to facts technology. Introduction to Facts Technology. Then types of facts controllers, facts versus HVDC, benefits of facts technology, performance equation and parameters of transmission lines, transfer of active and reactive power over a transmission line, uncompensated transmission, need for compensation, definition and function of compensation. So this is what we will be covering in module number 1. So therefore I will advise all students to just revise their power system courses, because especially transmission lines, transmission networks, flow of power on transmission lines, stability, steady state stability, transient stability, power angle characteristics, power equation, and so on. So that is the prerequisite for understanding this course. So this is what we will cover in module 1. Then module 2 will comprise of following topics like we'll discuss various compensation techniques like ideal shunt compensation, ideal series compensation, phase angle control, that's phase angle regulator, advantages of series compensation, voltage support, transient stability improvement, power oscillation damping, advantages of shunt compensation, thyristor controlled reactor TCR, thyristor switched capacitor TSC. As far as this TCR and TSC, that is thyristor controlled reactor and thyristor switched capacitor, are concerned, they are part of the FACTS controller, which is called SVC, static wear compensator. They are the components of that. Then in module 3 we will discuss analysis of various types of static wear compensators, SVC, static synchronous compensators, STATCOM, analysis and comparison with SVC STATCOM converters. We will discuss STATCOM converters like multi-level voltage source inverters for STATCOM applications, series compensators like GTO controlled series capacitor, that is GCSC, thyristor switched series capacitor TSSC, thyristor controlled series capacitor TCSC, static synchronous series compensator SSSC. So main series and shunt compensators will be covered in module 3. So it will be a fairly long module as far as various types of FACTS devices or FACTS controls are concerned. Then in module 4 we will discuss voltage and phase angle regulation, thyristor controlled voltage regulator TCVR, thyristor controlled phase angle regulator, that's TCPAR, series shunt compensator like unified power flow controller UPFC, series compensator like interline power flow controller IPFC, and then thyristor controlled braking resistor TCBR. And we will also try to do mathematical modeling of some FACTS controllers. In fact, whenever we try to study any type of FACTS controller, whether it's a series compensator, shunt compensator, or series or series shunt compensator, its analysis will be enhanced by mathematical modeling during the discussions itself. The various textbooks that will be, I suggest you to follow for this course are, there is one very good book, Understanding Facts, Concepts and Technology of Flexible AC Transmission Systems by Hingorani and Gyugi. Hingorani and Gyugi, they are considered the pioneers of FACTS technology. Another book is Thyristor-based FACTS Controllers of Electrical Transmission Systems by Mathur and Verma. These are two main textbooks which I recommend you to follow for converter-based FACTS devices. Understanding Facts by Hingorani and Gyugi, it's a very good book. And for understanding thyristor-based FACTS controllers, you can follow Mathur and Verma's book. And for reference books are like FACTS Controllers in Power Transmission and Distribution by K.R. Padiyar. And I also recommend you some online NPTEL lecture series on FACTS, if at all it is available, and then journal and conference publications on this beautiful topic. Okay, so that was about FACTS, course title, course code, LTP, credits, and course contents. Like what are the various contents that we'll be covering in this course. It's one of the most interesting courses, very interesting courses you will see, and I assure you that I will try to make it very interesting. And when you at the end of the course, I would like to I will be very happy if my students feel that they have learned about FACTS technology, because the future of electrical power systems is FACTS technology. The global scenario is that these FACTS controllers are picking up very fast in Europe, in advanced countries, America, UK, France, Japan, China, etc. And in developing countries, including our own country also, these FACTS controllers are coming up very fast. Power Grid Corporation of India Limited, PGCIL Limited, they are on the job of installing various FACTS devices like SVCs and STATCOMs in various power grids across India. Okay. Let me try to define FACTS. Before we start this course, it is imperative for us to define FACTS. Definition of FACTS. I will give you two definitions of FACTS. One is, I will write here, a FACTS is a system composed of static equipment used for AC transmission of electrical energy. Let me first of all write the full definition. It is meant to enhance controllability and increase power transfer capability of the transmission network. It is generally a power electronics based system. It's of course a revolution brought by power electronics technology. So that's what I'm writing here. It's generally a power electronics based system. So my dear students, this is the first definition. A FACTS is a system composed of static equipment used for AC transmission of electrical energy. We are not using any rotating equipment like machines, synchronous capacitors or synchronous condensers, etc. It comprises of static equipment, and that static equipment is all power electronics based system. That may be thyristor based controller, that may be converter based controllers, and all that. And it is used for AC transmission of electrical energy. Actually, it is meant to enhance controllability and increase power transfer capability of the transmission network. If you have a transmission line, a transmission network, it can increase the power handling or power transferring capability of an existing power transmission network. And it can also make it highly controllable. I mean, you can control the flow of active power, you can control, you can make the compensation of reactive power. You can control the flow of active power through parallel or interconnected power transmission networks. That is the beauty of FACTS controller. So it enhances the controllability of power transmission network, and we can also increase the power handling or power transfer capability of the existing transmission network. So this is what FACTS is about. So FACTS is nothing but it is a power electronics based system. In fact, static equipment, which is basically a power electronics based system that's used for AC transmission of electrical energy, and it is meant to enhance the controllability and increase the power transfer capability of transmission network. So this is a concise definition of FACTS. IEEE has also given its own definition of FACTS. I will write there that IEEE definition also here. IEEE definition of FACTS. Let me write the IEEE definition of FACTS. IEEE defines FACTS like this. FACTS is defined as a power electronics based system. FACTS is defined as a power electronics based system, and other static equipment that provide control of one or more AC transmission system parameters. One or more AC transmission system parameters to enhance controllability and increase power transfer capability. and increase power transfer capability. So this is the IEEE definition of facts. It's very simple and a very lucid definition. Facts is defined as a power electrons based system and other static equipment. So it comprises of power electrons based converters or power electrons based other systems like thyristor based systems and other static equipment. When we say other static equipment, it may mean inductor banks or capacitor banks, I mean magnetics, which are also static in nature. And these power electrons based systems, along with other static equipment like magnetics, that is capacitor banks, etc., provide control of one or more AC transmission system parameters. Like they may control the transmission line impedance, which otherwise is very difficult to control, and they may also control the phase angle of power transmission system. What for? For enhancing the controllability and increasing the power transfer capability of the transmission system. So this is IEEE definition of facts. Okay, you will appreciate this definition only when you understand what facts is and why it is used, what are its main functions. So let us start Introduction to Facts Technology. Introduction. See, my dear students, nowadays we are operating highly interconnected power transmission networks. Throughout the world, power transmission systems or power transmission networks are interconnected power transmission systems. So interconnection is done. So interconnection is done, when we say that interconnection is done, what are we actually doing? We are pooling to pool the generating stations and load centers. In a country, we have large number of generating stations in different states, different areas. I may have a generating station here, I may have another generating station here, I may have another generating station here, I may have another generating station here, say in a particular region. What we are doing, we are pooling them together, we are connecting them together through a grid. And the loads which they are supplying, they are also interconnected, connected together, they are pooled together. So this is called interconnection. So pooling the generating stations, electrical generating stations and load centers. For what? For reducing the generation capacity, fuel cost, and improving stability of the system. Improving reliability, not stability, reliability of the system. This is why interconnection is done. We interconnect various generating stations and load centers together. We pool them together for reducing the total generation capacity. And when total generation capacity reduces, the fuel that we require, that also reduces. That's fuel cost also reduces, and it improves the reliability of electrical power system. You will understand it with the help of a simple example. Let us suppose we have 100 megawatt loads. So we have 100 megawatt load demand on a particular region. But loads are not at one place, they are at different places. For example, we may have 4 different 25 megawatts loads at 4 different locations. So, for example, this is generator 1. It supplies a load, say load 1. And how much is this load 1? This is 25 megawatts. So what we are doing, we are generating 25 megawatts of power here. It may be 100 kilometers away from the load center. And then this 25 megawatts of power is transmitted through high voltage transmission line, and then it goes to the distribution system, and finally this power is consumed by a load, 25 megawatt load. So this is a radial transmission line, isolated transmission line. It's not connected to any grid. It's not interconnected system. I may have another load here, say load number 2. its demand may also be, say, 25 megawatts. So what will I do? I will have a separate generating station and G2, and this will also generate power of 25 megawatts, transmitted over this radial transmission line at high voltage and supply it to this isolated load. Now you can see this transmission line and this transmission line, they are not interconnected, they are not connected to the grid, they are isolated. This is supplying one type of load and this is supplying a different load at a different place. The lines are not interconnected, loads are not pooled together, they are also not connected. I may have another generating station comprising of a number of parallel generating units. It may also generate a large amount of power, and it may feed at load number 3, which also requires 25 megawatts. So this is my load number 3. And finally, I may have another generating station at some other different location, which may supply load 4, whose demand is also 25 megawatts. So what is the total demand of these 4 loads? This load number 1 may be at one region, load number 2 will be at a different region, similarly load 3, load 4. Each load is supplied by a separate power station, separate generating station. Total demand of load is 25 plus 25 plus 25 plus 25, so it comes out to be 100 megawatts. So for supplying these 100 megawatt loads, separate isolated loads, we have isolated power generating stations. Each generating station generating a power of 25 megawatts. So therefore total generation capacity is also 100 megawatts. It's 25 plus 25 plus 25 plus 25, that's 100 megawatts. So these are isolated power systems. Now this isolated power system or isolated transmission networks, it has some serious drawbacks. One of the most serious drawbacks is that the generation capacity has to be very high. For example, your peak load demand of load 1 is 25 megawatts. Okay. Similarly, load 2, load 3, load 4. And you have, so we know that these loads show some diversity. Diversity means at any instant of time, load 2 may be requiring peak, and at that time, load 1 and load 3, 4, they may not be requiring, peak power of 25 megawatts. Let's say load 1 has a load of only 10 megawatts, load 3 has a load of or demand of only 5 megawatts, and load 4 has a demand of 15 megawatts, whereas load 2 has a peak demand of 25 megawatts. So this diversity of loads is not taken care of by these radial transmission lines, radial transmission systems, because each generator or each generating station has to have a capacity of peak load, that's 25 megawatts each. Even if load 1 is having a light load demand, say only 5 megawatts, but this generating station has a capacity of generating 25 megawatts. So large number of generating units are already installed there. Similarly at other generating stations. So that means the generation capacity is very high. Each generating station has a large number of generators, and each generating station has a maximum generating capacity of 25 megawatts. Okay. Second problem is that in the event of fault on this, for example, this system may have some fault. When this system has some fault, the power shutdown to the load will take place. Okay. You may have a fault here, or you may have a fault at generating station itself, and when there is a fault, no power will be supplied to this huge 25 megawatt load number 1. Whereas the other 3 loads, load 2, load 3, load 4, they will continuously get their power supply. But the system in which there is a fault, which results in shutdown of the system, shutdown of the generating station, all the load will lose power. So that means the system is not very reliable. Okay, a small fault on any of the generating stations or on any of the systems will result in complete blackout of that particular region. So what now we do, instead of having isolated radial transmission lines, we go for interconnection of these power transmission networks. For example, what we do is that we have various generating stations, say 1, 2, 3 and 4. The power generated by these generating stations they are interconnected together through long transmission lines. They generate the power and this power through long transmission lines is supplied like this. And we may have different types of loads, like we may have load 1, we may have load number 2, we may have load number 3, and we may have load number 4. You can see various generating stations, G1, G2, G3 and G4. They are interconnected with each other, and the various loads L1, L2, L3 and L4, they are also pooled together. And then we have these high voltage parallel transmission lines which are interconnected with each other. Now it has certain advantages. This is one excuse me. This is one type of configuration. Another type of configuration may be like this. We may have a generating station here, we may have two transmission parallel lines, we may have another generating station here, we may have load on this side, on this bus, and we may have load on this side. So this is also an example of an interconnected transmission system. We have generator G1, we have generating station G2, they are connected together, they are interconnected. And then we have load on this bus and we have load on this bus. At any instant of time, say for example, this load has a peak demand and this load also has a peak demand. So both the generators will supply power to both the loads. Suppose this load demand has decreased. So this power station G2 will not supply power to this load because its demand has decreased, whereas it may supply power in this direction to this load. Okay, because here you may have large demand, you may have a peak demand here which may not be fulfilled by generating station G1 alone. So this may supply all the power to the load and the remaining power may come from this side. Reverse may also be true. Reverse may also be true means the demand of this load may decrease at any instant of time and demand of this load may be peak. At that time, this generating station will supply all the power to this load and some power will be supplied by this generating station. Okay, so this is called diversity of loads. I mean, at any instant of time, you will always find that all the loads do not put their peak demands, maximum demands on the system. Load 1 may have a peak demand, load 2 may have very high demand, whereas loads 3 and 4 may have very light load demands at a particular instant of time. So because of that, the total generation capacity need not be 25 plus 20. I mean, this is 25 megawatts, 25, 25, 25, total is 100 megawatts. But at any instant of time, all the four loads together will not put a peak demand of 100 megawatts on the system. The peak demand may be only say 60 megawatts or 60 to 70 megawatts at any instant of time. So therefore, there is a saving of 30 megawatts. So how much generation capacity should we have here? We should have a generation capacity of only 60 to 70 megawatts because of diversity of the loads. Diversity of loads means that at any instant of time during day or during night, all the loads may not put peak demand on the system. Some loads may have very high demand, some loads may be very, they may put very light demand, very low demand on the system. So that will reduce the total generation capacity, and hence when the generation capacity decreases, so you are saving the cost, and the cost of fuel also reduces. The cost of electricity also comes down, it goes down. This is one advantage of pooling the generators and loads, that's interconnecting them. Another advantage is high reliability. Let us suppose at any instant of time, say generator G1, this station has developed some fault and it's not supplying any power. Or let us discuss this system. Say, let us suppose generator G1 has developed some fault and it has been shut down. Does it mean that this load will not receive any power? No. Because this load, although it may not receive any power from generating station G1 because it has been shut down due to fault, but some power it may receive from generator G2. Okay. Similarly, there may be a fault on G2, which means this load will still receive some amount of power, if not 100% of power, if not full capacity of power, but some amount of power it will receive from G1 through this transmission network. So this improves the reliability of your system. So therefore, the advantage of having interconnected transmission networks or interconnected power systems is reduced generation capacity, reduced fuel cost, reduced cost of energy, so cost of energy will also be low, and high reliability. So it is because of these reasons that we go for interconnected transmission systems, interconnected power systems. Okay, so I hope you have understood this. So that's why nowadays all transmission networks, all power systems globally, they are interconnected power systems. Now the problem with these interconnected power systems is that as the power transfers grow, as the power demands grow in interconnected systems, the interconnected systems, since a large number of generators, they are interconnected, a large number of transmission networks, they are connected to the grids, they are interconnected, so it becomes complex to operate them. So they become complex to operate, and they also become less secure to outages. I mean, outages means a fault. A small fault somewhere else may also result a disturbance in the region where there is no fault. So your system may become less secure, and it becomes very complex to operate. As a result of this, there will be large power flow without adequate control. Try to understand this sentence: large power flow without adequate control. That means, say for example, you have interconnected system like this. You have a load on this side, on this bus, and you have a load on this bus also. You have generators on both ends, and you have two parallel interconnected transmission lines. Say this is transmission line 1 and this is transmission line 2. There may be uncontrolled flow of power over these transmission lines. For example, let us suppose transmission line has a capacity of carrying 50 megawatts and transmission line 2 has a capacity of carrying 25 megawatts. It may so happen that transmission line 1 is carrying only 20 megawatts out of 100 megawatts, and transmission line 2 is carrying, say, 80 megawatts. Okay, transmission line 2 has a capacity of only 25 megawatts, but it is carrying 80 megawatts. So it is heavily overloaded and all the circuit breakers will trip. Okay, otherwise the system will get damaged. Transmission line 1, which has a capacity of carrying transferring 50 megawatts, it's carrying only 20 megawatts, so it is underutilized. Okay, so this may happen with interconnected power systems, and it has been seen that it happens. Okay, when you have parallel transmission lines, the power carried by a transmission line is inversely proportional to its impedance, to the impedance of the line. Okay, the lines with high impedances carry less power, and the lines with low impedances carry more power, and in this way some of the lines may get overloaded and some lines will be underloaded or underutilized. So that is what we call as large power flows without adequate control. So it will not be possible for us to control the flow of power through parallel transmission lines, through interconnected transmission lines. So this is one problem. Another problem is that there will be huge reactive power flow. Huge reactive power flow. Okay, you have a large interconnected system comprising of maybe hundreds of transmission lines, and load demand may be such that a large reactive load is there. So large reactive power will be flowing over this network of interconnected transmission systems. Okay, a transmission line is supposed to carry active power which is supplied to the load, but because of huge reactive power flow, the power transfer capability of the line will reduce. So this reduces power transfer capability of the line. So I will write here power transferring or power transfer capability of transmission line is reduced because of huge reactive power. When I say power transfer capability, it means active power. Since the lines are already carrying huge reactive power without any control, without any compensation, so it will have less capacity, less capability of transmitting active power. So that's what I have written here. Due to huge reactive power, flow without compensation on the transmission lines, the power transfer capability of the transmission lines will be reduced. So this is another problem. And the third problem is that a small fault in the system will result in huge power oscillations in the interconnected systems. There will be power oscillations. And the system will be less secure because of these oscillations, and it will have reduced transient stability. Reduced transient stability, which means that a small fault may render it unstable. The interconnected power system may become unstable even by a small disturbance. So these are some of the problems with interconnected power systems. I repeat, one of the problems is that there will be large flow of power without adequate control. We will not be able to control the flow of power over various transmission networks in the interconnected system, because of which some of the transmission networks may get overloaded and some lines will be underloaded or underutilized. And because of uncontrolled huge reactive power flow over the lines, the power transfer capability of the transmission lines will get reduced, and then there will be power oscillations which will make system less secure and reduce transient stability of the lines. Okay. Now for reactive power compensation, as you know, almost all the power systems, they go for reactive power compensation. But these reactive power compensation systems, they use capacitor banks. We are using capacitor banks. So at any instant of time, we may be asked or we may be required to switch in some capacitor banks, and at some other time switch out the capacitor banks in steps. But the problem is that these compensation circuits or capacitor banks or inductor banks, they are mechanically controlled. Mechanically controlled. And when I say mechanically controlled, that means the switching devices through which a capacitor bank is switched in or switched out, the switching devices are mechanical in nature. We are not having static electronic switching devices. They are mechanical in nature. So we have mechanical devices which may switch in some capacitor banks for reactive power compensation, or which may switch out some capacitors when large reactive power compensation is not required. Since these switches are mechanical in nature, so they are sluggish. Their response is very sluggish. At any instant of time, for avoiding the power oscillations or for transient stability of the system, we require very fast action. I mean, as soon as a disturbance has come, we require that the compensation should very quickly take place. But these mechanical switches are very sluggish in nature. They are very slow in response. So therefore our systems, they become mechanical in nature. And when I say mechanical in nature, they are not able to do the corrective action in time, and which makes system insecure. Okay, so proper compensation will not take place. The system will be insecure, and it will be, when I say insecure, it will be less stable system. Okay, so this is another problem with modern interconnected power systems, that the compensation circuits like capacitor banks are mechanically controlled, and these mechanical switches are sluggish in nature, and hence the systems become less stable. Another problem is that as power demand increases, because with every passing year the power demand increases because of increase in the population and because of increase in the loads, power demand increases. You may have to go for new transmission networks. You already have some transmission networks, but those transmission networks may not be sufficient to supply the increased demand. So you may have to go for laying of new transmission lines, new transmission networks. But nowadays it will be very, very difficult to acquire the right of way, because for laying a transmission line you need a huge land. Okay, you need land, and you have to procure, you have to purchase the land from farmers, you have to cut the trees, and you have to erect the transmission towers over hundreds of kilometers, and you have to lay the transmission lines. So acquiring right of way, which is also called ROW, is very difficult nowadays. It's very difficult. If you have to establish, you have to design, you have to erect new transmission towers, you have to set up new transmission networks, you need a large amount of large land. For that you have to acquire the right of way. It's a difficult task nowadays. So will facts help us? Yes. Facts technology helps us in alleviating some of the problems which I have discussed. One of the problems is that there will be uncontrolled flow of active power over various transmission networks, which will make some lines overloaded and some underutilized. Second is that there will be uncontrolled reactive power flowing over the transmission system, and hence it will decrease the power transfer capability of the transmission lines, right? Third is that power oscillations, the transmission systems will be subjected to the power oscillations even by small disturbances. Fourth is that our transmission system will be less reliable. The transient stability of the system, it will be less stable, not less reliable. Its transient stability will not be very high. So hence it will be unstable system. And then since our transmission systems are mechanically controlled, the response is slow, and hence that will also render it unstable. And finally, for meeting the extra or increased power demands or load demands, you have to lay new transmission networks, for which you have to acquire the right of way, which is difficult nowadays. The question is, how will facts technology solve these problems? Answer to this question is yes. Facts technology, that's flexible AC transmission system technology, which is a power electronics based technology, alleviates some of these problems, some of above mentioned problems. Okay. First thing, what facts controllers will do, they result in power flow control. Actually, what facts technology does, whenever you use a facts controller, whether it's a series facts controller or shunt facts controller, it controls certain transmission line parameters. Okay. What are the transmission line parameters? Transmission line parameters are series transmission line impedance, or its shunt impedance, or its voltage or current or phase angle. With the help of facts devices, we can control the series impedance of transmission line, we can control its shunt impedance, we can inject the voltage into the transmission line, we can inject the current into the transmission line, or we can control the phase angle of a transmission network. By controlling these parameters of transmission system, we will be able to control the power flow over various transmission lines, and hence the problem that there will be large power flow without adequate control, that problem will be altogether solved. There will not be power flow without control. By controlling these parameters with the help of facts controllers, we will study how we can control these transmission line parameters, inshallah, in future lectures with the help of facts technology or with the help of facts devices. By controlling these transmission line parameters, we will be able to have perfect control over flow of power in interconnected transmission networks, so that none of the lines is overloaded and none of the lines remains underutilized, right? So this problem is solved by facts technology or facts devices. Another advantage of using facts technology is that it results in perfect Q compensation. Q compensation means reactive power compensation. Here also we use capacitor banks for injecting reactive power into the system, but the system is not mechanically controlled. Using facts technology, it becomes electronically controlled system, and electronic control is very fast. Within one cycle or two cycles, it will do the reactive power compensation, and very fast compensation it will do. And when it does the reactive power compensation, that way it improves or it increases the power transfer capability of existing lines, increases the power transfer capability of existing transmission lines or transmission networks. So if your load demand has increased, say after 5 years your load demand increases, you don't need to design new transmission lines. You don't need new transmission networks, because acquiring right of way is very difficult. So the existing transmission line can be made to transmit more power by FACTS technology, by FACTS devices, because what FACTS devices do, they do perfect reactive power compensation, and hence they increase the power transfer capability of an existing transmission line. So the existing transmission line can itself be used for transmitting more power. So therefore you don't need additional transmission networks. Okay, how they increase the power transmission capability of transmission lines, I mean how FACTS devices increase the power transfer capability of existing transmission lines, I will discuss with you in details. Okay, don't worry about that. We'll be discussing that in future classes in details. Okay, FACTS technology or FACTS devices will be also damping power oscillations perfectly. Okay, whenever there are some disturbances, your transmission system or network is subject to power oscillations, but with the help of FACTS technology, FACTS devices like series compensators and shunt compensators, the oscillations can be very quickly damped out, and hence your system becomes more stable and more secure. Okay, your system becomes more secure. And they also improving transient stability of the system. Transient stability. Okay, by using shunt compensators or series compensators, which are various types of FACTS devices, the transient stability of a transmission network or a transmission system, or the transient stability of a power system can be significantly improved, and hence your system becomes more stable. So these are some of the advantages, some of the tasks that can be performed using FACTS technology. With the help of FACTS devices, we can have perfect control over active power flow, we can compensate reactive power flow, we can hence improving voltage regulation at buses. By controlling the reactive power, the voltage regulation can be improved. We can also damp the power oscillations very quickly with the help of FACTS devices, hence we make the system more secure. With the help of FACTS devices or FACTS controllers, the transient stability of the system is also improved, and finally the voltage regulation can also be improved by providing the voltage support. Now the only problem with FACTS technology, FACTS devices, is cost. Presently, cost of FACTS devices or cost of FACTS technology is very high. It's very high. That's the only impediment or roadblock, especially for poor countries. But as the power semiconductor devices will improve in future, and as the use of FACTS devices advances more and more, it becomes more and more widespread. Let me tell you, there will be widespread use of FACTS technology in future. Or I would like to say the widespread application of FACTS in future is an assured scenario. It's an assured scenario, which means that in future, 5 to 10 years down the line, all transmission networks will be enhanced by FACTS technology, by FACTS devices. So this was a small introduction to FACTS, the definition of FACTS, flexible AC transmission system, why do we go for interconnected systems, transmission networks, what are advantages of interconnection of transmission networks, and what are the challenges posed by these largely interconnected transmission systems, like uncontrolled flow of power, large reactive power flow, and then limited power transfer capability of the line, less stability of the line, and so on. And then I have tried to explain how FACTS technology can solve most of these problems. Like using the FACTS devices or FACTS technology, the active power flow over various parallel transmission lines can be controlled. We can have a perfect control over active power flow over the lines, interconnected lines. hence ensuring that none of the lines is overloaded and no line remains underutilized or underloaded. And then reactive power compensation can be very quickly done, and hence voltage regulation of the buses can be improved, voltage support can be provided, and then the power transmission or power transfer capability of existing transmission networks can be improved, and hence you don't need new transmission networks. The existing transmission networks can be made to handle more and more active power as the load demand increases. Then improved transient stability and damping of power oscillations. So these are some of the main advantages offered by FACTS technology in our highly interconnected power systems. So inshallah, in our next lecture, I will try to explain how active power flow control can be achieved, or how power flow control in interconnected network can be achieved with the help of FACTS devices. And we will also try to classify FACTS controllers or FACTS devices into various categories. With this, I will end my today's lecture. This was just an introduction to FACTS technology and an introduction to this subject. Please go through this lecture and stay connected. Thank you.